today I'm going to be talking about effective use of the Mathematica compiler and code generation. And there's all sorts of stuff I could do with this. So basically what I've done for this talk is I've prepared 3 examples, of which I actually expect to get to 2. And you'll be able to get the talk notebook and see the 3rd example. It's a little bit of the similar vein as the other 2, but I tried to sort of pick 2 semi-realistic examples to show sort of at least the process I would go through in actually compiling a function. And I think this gives you an idea of how you can use the compiler's feature and our code generation somewhat effectively to speed up your Mathematica program. So let's go right into it. So there's a Mathematica function called compile, and you may never have used it directly. In fact, a lot of people hasn't, but it's actually sort of under the hood for a whole bunch of things in the system. It's used in plotting functions, for example. So a lot of these plots you see that come out very fast, like Stephen's plot of the membrane with the finite element method. The reason that plot is fast is because it actually compiles the function in and evaluates it quite quickly. It's used for all the numerical computation functions like ndsolve, find root, so on and so forth. It's a huge part of doing that to make it really fast to evaluate the function. So we sort of process a function at the beginning. Part of that processing is actually compiling it if it does compile, and then just repeatedly evaluating it that's a very common use. And it's also like a part of the Mathematica code system. So like if you do map of some function on a big list, it may be auto-compiled if the list is long enough and the function is amenable to compilation. So those are all sort of automatic use, and that speeds up the language quite a bit. In fact, we get questions in technical support not infrequently as why is it changed? Why is it so much faster at size 250 than it is at size 249? Well, that's because we have these thresholds to decide when to compile, and you can change those if you really want to. So again, the compiler there is used to speed up. And a key part of this thing, and this is something I'm going to emphasize in this talk, and I'll probably harp on it. You'll get sick of me, but you'll have to put up with it anyway. Is it's speeding up just a part of the computation at once. So I'm not trying to compile a whole code. Like when you do C, you have to write a whole code. You have to write a main program and something that's going to call, and a library, and so on and so forth. Well, in Mathematica, you don't have to do that. You don't have to compile the whole thing. You can compile one tiny little piece of it, and if that's the piece that's slow, by compiling it, you're going to speed up your whole program. And that's kind of a key idea. So you don't have to think of it as C or Java or a language where the whole thing has to be compiled. Most of Mathematica is interpreted, and a lot of Mathematica is most appropriate as something that's interpreted. Okay? And the compiler is actually just a different special interpreter or virtual machine. So you don't have to do it. And an important point, I'm going to make this again, is that the interaction, so in version Mathematica 4, we introduced this thing called packed arrays. Okay, and that sped up all sorts of computations. It made it possible for us to solve partial differential equations, which was my love, and lots of other things. And the way we designed the packed arrays is to use exactly the same list structure that was already internal to the compiler, that had been introduced in version 3 into the compiler. So packed arrays and lists within the compiler are identical. In fact, they share the memory. So going from a packed array as a compiled argument is really fast and efficient. So having 3 compiled functions may not be any more efficient than having a single one that wraps your whole program. And I'll make that point a few times as I go through this talk. So before I actually get to the example, I'm going to point out some things that are worth keeping in mind. Again, I'm saying it again, you don't have to compile the whole program. Absolutely essential. Okay, the internal data structure for lists in compile is exactly the same as the internal data structure for packed array. And so packed array in and out is really efficient. And there's essentially nothing lost. Sometimes a copy has to be done. Okay, and then this is another, so the way Mathematica compile works, I'm not going to really go into the details here, but Mathematica compiles a set of Mathematica code into a set of sort of pseudocode instructions. And then there's a virtual machine which runs on those pseudocode instructions. You'll see some examples of printouts of those pseudocode instructions, so you'll understand that a little bit better. So when I refer to the virtual machine, I sort of refer to the machine that actually interprets these pseudocode instructions. Okay, and it turns out one of the things we set up with version 8 is we set up a new template for calling functions of the virtual machine, which made it much easier for us to extend the functionality the compiler covered, okay? And also, we decided to make that template internally to the compiler identical to the one that's used for Library Link. So if you've ever done, and there will be a talk, Todd Gailey and Joel are giving a talk about using Mathematica with C sometime later in the conference. So if you're interested in getting really fast functions, so you can actually call any Library Link function from the compiler with essentially no loss of efficiency. And so there's sort of two ways that the compiler can interface with the system or extensions of the system that are very, 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 very efficient. Okay, another point about compiling is that compiling in listability. So listable functions are ones that sort of thread over arithmetic, like sine and plus and times. They just automatically work on lists. Well, you can use an option of the compiler, and I'll show this in my examples, that gives a compiled function the same listability. And that has a bunch of advantages. One, it's flexibility. So a single function can work for lists or scalars or nested lists or matrices or tensors or whatever. Okay, and it just threads over it automatically. Another flexibility advantage is it is a way to work around the restriction that nested lists in the compiler be rectangular. So you can use that sometimes to your advantage when you need that. And then finally, speed is when we use this listability in the compiler, it's automatically parallelized. So you get, if you have a machine with more processors than this one, you'll really see some advantages for that. Okay, so compiling to C code, and that's the code generation, is, and I'll give examples of this, it can make things much faster to evaluate, but you have to keep in mind that the C compilation itself can be very expensive. So you have to think about the context in which it's being used as to whether it's actually worth compiling to C or not. So don't just assume that using C compilation is always going to be better than the virtual machine. Sometimes it is, but sometimes it's not. Okay, and if you're actually going to be using the compiler, developing code, I suggest two things. Turn on compiler warnings, okay, and that'll give you warnings about things the compiler doesn't really know or it has to guess on, or cases where it's not going to be quite as fast. And I also suggest using compiled function tools. There's a particular function in there, compile print, that I'll use in the examples. That'll show you what the compiled function is actually doing. So if something's not working as fast as you expect, you can actually see what it's doing and what's going on. Okay, so now to the examples. So the first example, I'll do a pretty simple one where we're going to try and design a function that does Chebyshev approximations. So given an interval x0, x1, I want to represent a function f of x on that interval as a sum of Chebyshev polynomials. Okay? Now it turns out that's really easy to do in Mathematica. So why do I have to give, as an example of my talk? So the way you do it in Mathematica is I can just design this function as follows. I say t-sum, yes, I better evaluate all those things. So basically all I have to do is I've defined the function to actually take the variable f of x. This is just actually using the display. These are going to be the coefficients of the Chebyshev series. And what I do is, given an interval, I scale to put on the interval -1 to 1. This is where the Chebyshev evaluation is going to be the most stable. And then I just sum it up with a function t-sum. And the t-sum is really easy. It's just a table of the Chebyshev functions over the length of the thing. So it couldn't be simpler. Except this version has a little bit of a problem, which we'll see soon. Okay, and to make things more fun, I put in a little pretty printing form so that you don't have to look at all the coefficients. Now I'll make a function that converts some arbitrary function into one of these Chebyshev approximations. And I won't go, the math of that is great, I love it, but no time. So just trust me that it works. And then let's try an example. Well, a good example is Runge's function, which with ordinary interpolation oscillates uncontrollably. So here's my representation. I've used 47 coefficients. that was just arbitrarily picked because 47 is a magical number. And now we can plot the function and its comparison. So the little bit of wavy one is the Chebyshev function, and this is the actual function. So it's pretty close. Now, to get much closer, I'd obviously have to use more coefficients. And with some work, this could be a start of a package which would you sort of automatically use error estimates to try and get the right number of coefficients in a given interval, and so on and so forth. But I'm just sort of concerned about the evaluation stage here. So let's try it. So let's take a random list of 10,000 values, sort of between 0 and 2 pi, which is where I define that Runge's function, and let's see how long it takes. So if you think I'm obsessed with timing, well, I am, because that's partly how I work to try and make Mathematica fast for all of you. So I'll show lots of timings in this talk, but actually that's a big part of figuring out how to use the compiler effectively, is time things, test it, see what actually works, see what doesn't. Okay, so that's just doing this function. And there's also another way I can do this, and that's using it listability. Okay, so if we look back at the definition of tsum, which I probably hid. No, it's right here. Okay, Chebyshev t is a listable function. So if x is a list, it'll automatically go into that, okay, and it'll just work as a list. Those will all come as a list instead of use the dot product. It'll just come out correctly by vector matrix multiplication. Okay, so listability just works for this version automatically. Okay, so, but really if the approximation is going to be useful, part of the idea of the approximation is that it's going to be as fast, or not a whole lot slower than the original function for something simple like this. But let's compare it. Oh my gosh, that's a lot faster. And if we use listability, that's even worse. I mean, so we've gone from something that takes, 0.0004 seconds to like 1.7 seconds or 1.8 seconds. That's pretty horrible. But we can do better, okay? And this is where the compiler comes in. Okay, there's actually a couple things that come into this. Okay, first, there's two reasons that it's slow. First, that evaluation of the tsum is done without the compiler at all. Okay, so it can be sped up. Now, as is, it couldn't be sped up. One of the reasons it's so slow is another complexity reason. Okay, and that is that if I sum up the t0, t1, calling Chebyshev function in Mathematica, Chebyshev t, well, it has to evaluate all of those separately. Well, it turns out there's a really nice recursion that allows you to sort of sum up a polynomial of this, and it's called Clenshaw's algorithm. Okay, and what Clenshaw's algorithm looks like, and I'll just do it, since I know I want to compile things, I'm going to do it at this point as a compiled function right off the bat. And I'll call it Clenshaw VM because it's going to run in the Mathematica virtual machine. Okay, and so what this is, and again, fun mathematics, I put a link on the previous page that gives you a page that kind of goes into the basic mathematics of it. But basically, this is just a way of using the recurrence for the Chebyshev functions to get the sum of the polynomials. So you kind of evaluate each polynomial in succession, and it works. So we avoid the complexity problem, and by compiling, we get a compile. Now, the one thing I'll add here is I use runtime attributes goes to listable, which is one of the things I suggested. Well, I want that function to be listable, kind of like the tsum I originally had. So I add that attribute, and what will happen is, notice here I say, okay, the coefficients are a list. Okay, so underscore real 1 means they're real values with a rank 1, so that's like a vector. And I could put 2. If I don't put a rank like I did with the x, that means it just expects a scalar. But when I add the runtime options goes to listable, if x is now a vector instead of a scalar, it just automatically runs that repeatedly for each successive value of x. Okay, and if you have lots of processors and the function doesn't have some weird stuff in it, it'll automatically parallelize over your processors doing that. So you get sort of a couple of benefits. So let's replace that tsum definition with my Clenshaw VM. Okay, and now, just by doing this, I mean, a big part of it was Clenshaw's rule, but another big part of it is compiling it. I'm down to 0.209 seconds. Okay, from it was 1.9 before. okay? And if I do the listable version, I'm another factor of 10 faster. And this is where using this runtime attributes is listable. If you have something that you want to be able to list, not only is it flexible, but it gives you a huge speed advantage. So I'm almost a factor of 10 faster just within the compiled function over doing the map. OK, so now let's go to the next stage and say, OK, well, that's all good. Let's see what happens. This is going to be, say, if I write a package that's going to evaluate these things, I basically only have to compile this once, and then it can be used again and again and again for every time I approximate the function. So that's a case where it is worth the extra time to compile to C. Or if Abdul ever gets to it and we get our discussion, he'll have it compiled to CUDA, which will be great. We're thinking about that and working on that. So maybe we could parallelize on a GPU for something like this. OK, so basically, I kept the runtime maps and I added compilation target C. So what this does is this goes, it generates the bytecode, and then it generates a symbolic C module. OK, and then from that, it writes out C code, and then it calls a C compiler on your machine. And it's meant to automatically compile, set the right compiler without any real setup time. And then it sets that up as a library link function, and then it links it back into the compiler. So the compiler evaluation is done through library link instead of the compiled virtual machine. So let's change that. OK, so now if I do this map, I'm down to 0.18 seconds. So that wasn't a huge change. OK, but let's look at the listable version. OK, and here, so I went before it was 0.24. And now I've gone to 0.0068. So I've gained nearly a factor of 4 by compiling this to C in the listable version of this. Now I can do better than that. So when Mathematica evaluates, we're getting better, OK? But the thing is, when you look at your function, you should think about what it's doing. So this is going from runtime options goes to speed, says do everything as quickly as possible. So we don't, Mathematica by default does underflow checking, overflow checking, and the default from the compiler is to do overflow checking but no underflow checking. And by speed, I say don't do any of this checking. It's too expensive. And for this function, I really don't care if it underflows. And if it overflows, the approximation is not going to work anyway. And I don't want to try and evaluate it. And so I say turn it all off. Let's see how much faster we can be. So I do that. And then we do this, and we're down to 0.17 seconds for that one. For this one, we're down to 0.001 seconds. So we got an extra factor of 2.5 or so. And that's on top of a factor of 3 to 4. So we're talking about a factor of 6 or 7 by compiling to C with the runtime options goes to speed. Now, not all functions will get this amount of benefit. It depends. So you have to trade off between how expensive it is to do and so on and so forth. So now I'm going to include a version that actually includes the scaling, because that turned out to be very expensive in the other one. So I put in the scaling. So I put in an argument x. I put in the x0 and the x1, so the interval endpoints. So this does the scaling and Clenshaw's algorithm all in one. So that's and so if I change that to use the tfun, and then I do the map. Now the map version is quite a bit faster than it had been. I get almost a factor of 5 by doing that. And then the listable version is not any faster. In fact, it's actually a tiny bit slower. Okay? And the reason for that, I should just show this, is, and this is why you don't necessarily want to compile everything. Now in this case, I think it's worth it because we get so much speed for the single use case. The reason is this operation, x equals 2s times minus this, if you do that as a listable thing, that automatically calls MKL functions, which automatically parallelize, and probably in a more efficient way than the compiler level parallelization does it. And because the output is for x a packed array is always going to be a packed array, the interface with the compiler is completely efficient. So there's no loss whatsoever. So for the listable version, it's slightly slower to do the scaling in the compiler, but I'm willing to pay that to get the extra speed for the single use case. OK, so now what I'm going to do, and I think this is a lesson I hope you can take out of this talk, is I'm going to make a function I call Clenshaw. OK, and this is actually just going to do it. So I'm going to set up now a package that does it for any precision. okay, and show you how to integrate that with the compiler. So I started out with the compiler, but this is the way to effectively, so this is exactly that Clenshaw's rule, okay? So I take a function like this, and here I've actually included the scaling in this inside the module. So now here's a trick, okay? I'll call this Clenshaw compile. I'll take the type I want to compile to, and I'll take a function. And note this could actually be just about any function with the same arguments, and this would actually compile any function with the same arguments. It doesn't have to be Clenshaw's function, okay? Because that's actually in the pattern for the thing. What it does is it takes the arguments, it adds the types to the arguments. Some of the arguments are going to be real, like the x0, x0. Some of them are going to be according to the type you want. And this type, for our purposes, is going to be real or complex. Okay, it just compiles it, and I use all these fast options to do that. Okay, so I set that up. Okay, and then I set up two functions, one which I'm going to call Clenshaw R for reals and Clenshaw C for compiles. And what this is going to do, notice this is a delayed setting. So only when it gets used do I reset its value to be the actual compiled value. So this means that if nobody ever uses this, I don't pay for the compilation to C, though in this case it's not that expensive. But for a big program, it could be quite expensive. Or if I never use a complex version, I don't have to pay to compile that. It's only when it actually gets used. So this is a really nice way to set things up with Mathematica values. I'll clear tfun, start over again. I'll basically reset all the values, kind of like I did before, except now if I check the input, if it's a packed array of reals, it uses, if the coefficients are real packed array, it uses the real version, complex version, or I coerce to the precision I give, and it uses the outer version, just the function version that's not compiled in that precision. So this is an adaptive function that works with adaptive precision. So let's see if it actually works. I rewrite the T2 tfun so that it takes a machine precision, working precision option, like many of the numerical functions. So let's try it on a function. So good, that worked. So I'll do a hypergeometric function. So to generate that function, it takes about 0.18 seconds, okay? And it actually works. But let's try it again now. Because that first time I used this function, it had to do the C compilation. So if I do it again, the second time, it's a heck of a lot faster. Okay? And every subsequent time you use it, it's going to be faster, the same speed again. Okay, and I didn't even get to the second example, given time, because I spent too much time on that. So in any case, this example is about making a fixed-step ODE. And if you have time to look over the talk notebook later, I recommend, because it talks about how to call functions that are external to the compiler and sort of inline those. And that's another important point for effective use. And then there's one other example about a simple method for the pendulum equation too. Okay, so in interest of time, I'll just go directly to the summary. I think that Chebyshev example was my favorite one because it actually shows something you can really do with the compiler. But I don't have to compile everything. I just compile that tfun part, and it works really effectively. Okay, so one thing is to be a little aware of types, use compiled functions, prick compile, and there are examples of that in there if you look at that. Okay, you could speed things up, and some things to do are try to avoid Mathematica evaluation, check type consistency, and again, think about runtime attributes goes to listable. You can also set parallelization goes to true, though often automatic does exactly what you want. And if you expect to use a function many times, like I did with that tfun thing, try compilation target goes to C. Okay? And again, I'll emphasize as a final thing, what I think is the most important thing at all, you'll have much better success in using the compiler to speed up little parts of the computation than trying to compile a whole big program at once. Use the interfaces that the compiler has to the rest of Mathematica to make it easy to compile things instead of making it as hard as possible. So with that, any questions? And I should get out of here so the next speaker can talk.